Okay, so let's get started. Hello, everyone. Welcome back to the Advanced Machine Learning lecture series. We are now close to the finish line. So it's just today and on Wednesday. So we are at the end of this lecture series, and I want to come back to something that we started discussing briefly at the beginning. So if you remember, at some point we had this picture where we said that when people started to investigate nature, they would, for example, look at the night sky and they would try to discover regularities and make up models for what they see. And they came up with models, all right. At first, they were a little bit complicated, but then over time, they realized that they could replace these models by simpler models, which could even explain more data than the original rather complicated models. And so this is something that we want to discuss today and on Wednesday, namely how to make predictions, how to reduce the amount of complexity needed in your hypothesis, and how to do that in a mathematical way, so to speak. So the chapter I've entitled Complexity and Prediction and Occam's Razor. So the goal is to make predictions based on past observations by detecting regularities and providing therefore efficient descriptions to go ahead and predict the future. And Occam's Razor is, of course, the principle that you want to choose, typically the hypothesis with the lowest complexity to make these predictions. And so then we have to discuss, what does it mean, complexity? How do we even quantify this? And all of this more formally is known as the field of algorithmic information theory. It has connections to what we discussed before. For example, when we discussed Shannon entropy, we understood that entropy in this information theoretic sense can be related to the amount of compression you can perform. And you could potentially view science or the art of making good predictions as a scheme to make good compression. And as we will see later, what we are discussing will also be related to Bayes, and we just come from discussing how to apply Bayes in order to understand experiments and to make predictions for experiments. Okay, so let's get started. Suppose you make this sequence of observations. So the sun rises one morning, then night falls, you have the moon, then the sun rises again, then night falls again. And this goes on all the time for many days. And on the day number 12, you are expecting in the morning the day to start again with a sunrise. But what justifies this expectation? Yeah? And the answer that we would have is that it seems quite reasonable that a regularity that worked so well to explain all the past observations should also hold in the future. But the question is, how can we make this more precise? Now, when we want to discuss these things mathematically, we want to simplify the description as much as possible. So the sequence of observations that we are going to consider in the following, that will always look like a binary string, because we can basically represent anything as a binary string. And here I've collected a few binary strings. And so the question is now, can you imagine how these strings continue? And so in the first string, you would see immediately there's a pattern. And of course, you would imagine that this pattern will continue, even though, importantly, there is no guarantee for that. Now, in the second bit string, you see something rather arbitrary looking in the beginning, but then again, there is a pattern. So again, maybe you would make the same prediction. In order to compress the whole situation, you would need a little bit more information, more bits, but that's the only difference. And then the third example is, of course, one where there's an increasing number of ones if you look closely. And so again, you would have a simple prediction. So in all these cases, we would imagine we could write a simple program to produce this regularity, and then we could use this program to make our next prediction. And hopefully we would be right, but there is no guarantee. And then there's the last example here, which I hope really shows a completely random sequence, but that raises the more general question, how can we decide when is something random? It seems obvious to us here, but how can we make this precise mathematically? So these are the kinds of questions we want to study. And in this whole business of making up a hypothesis in order to perform predictions, Occam's razor is mentioned as a guiding principle. Now you have to understand this did not originate with William of Occam. It came about much, much earlier. Even Aristotle and Ptolemy are already talking about that. The basic principle is that if you have some observations and you seem to see some regularities, you want to make a hypothesis, and typically there are many hypotheses to explain the same observations. And this principle then states that you should prefer the hypothesis or the model that is simplest. So prefer a simple model. This immediately, of course, raises the question, what do we mean by simple? And you could imagine, oh, this means that to describe this model or hypothesis, a short description is sufficient. But then again comes the question, what does it even mean to have a short description? Doesn't that depend on the language in which you write down this description? And indeed, all of these questions are valid questions, and these will concern us. Okay, so before we go to the more general discovery of regularities, let's come back to something that we maybe neglected a little bit during these lectures, which is symbolic approaches. So we had neural networks to approximate arbitrary functions and then to fit to the data that we have using gradient descent and some loss function that measures the deviation between the predictions of your model and the actual data. But of course, when we do something like theoretical physics, we like to express hypotheses in terms of symbolic expressions, and then we derive symbolic expressions from given formulas, we derive new ones. So it can be very useful to phrase our knowledge in terms of symbolic expressions. So how do we even represent them typically? Well, that's in terms of expression tree. It's a tree structure. So let's discuss that for a moment. If I want to store a mathematical expression in my computer memory, the computer would typically do something like this, a tree where, for example, the plus sign is put here, and then there must be two terms that I will add. Maybe the first term is really a product of something, and it's the product of, say, the variable x and a sum, say it's the sum between 3 and y. So already this left half of the tree, I could write down the expression for that. It would be x times 3 plus y, just copying, just translating. And then on the right part, we might have something else. Maybe there's a division sign, and maybe then there's a constant like pi. There's another x. So I would have something like pi over x. So this would be the tree corresponding to this particular expression. And so now what you could do is, of course, if someone gives you a function f of x, and that is the function that you are given, maybe also only in terms of a few data points, or maybe somehow completely, you can call this function as a black box routine, then your goal could again be to fit this function. But instead of trying to start from some parameterized family of functions, or to start from a neural network with its many weights and biases and to choose them correctly, you could also simply try all possible symbolic expressions in a certain family of expressions. It depends on how you define the details, which numbers are allowed, which operations are allowed, and so on. But you could try all possible symbolic expressions that have x as an allowed variable inside them. And then these would give different curves. So this would be one curve. Obviously, it doesn't fit very well. That would be another curve. That would be one curve. And then finally, hopefully, you would find some curves that come pretty close to the function you're trying to fit. So this is something you could do. And this is actually something that people have done. So try to fit using some symbolic expressions that include x. Now the question is a little bit, how do you even search through all these symbolic expressions? Because there are obviously infinitely many of those. And one kind of reasonable way would be to constrain the number of nodes, that is the number of these nodes that are either operands or variables or numbers, and to first start with a small number of nodes, consider only the small trees, and then go to larger and larger trees. And of course, you would expect that the more nodes you have, the more terms you have in your expression, the more easy it should be to fit. So if I now quantify the quality of the fit, which I could do, for example, by measuring the mean squared error, just like we do for neural networks, then how would this look like? So I would start to plot the mean squared error, mean squared deviation between the actual function and my symbolic expression. And I would plot this as a function of this number of terms. And so, for example, I could fix the number of terms to only 2 terms, so very simple expressions. And I try out all of these. And of course, I get many different values for the mean squared error. But all of these values lie above a certain point. I don't get better than that. There's an optimum. And then I increase to 3 terms. And again, I observe the same pattern. And again, there will be an optimum. And this optimum will be typically better. And then I will go to 4 terms and so on. And what I will see is that I have a dividing line, so to speak, between the, so this is discrete, but anyway, a dividing line between the upper area where I do get mean squared errors. So these are bad models, bad fits. And the area below where I have no fits of this quality at all. And so what we could observe in a typical example is maybe that at some point we really touch down to 0. So that would be finally where we find the first symbolic expression that really fits our function. This is not guaranteed. Maybe you have chosen a very nasty function which simply cannot be fit at any number of finite terms, but it can happen certainly. And so this kind of behavior is part of a more general concept. In principle, we are trying to optimize 2 things. On the one hand, we would like to have a small mean squared error. On the other hand, we also would like to have a small number of terms. And these are in conflict with each other. So if you want to decrease the number of terms, unfortunately, you also have to increase the mean squared error. That's the compromise you have to do. And so it's a typical example of trying to optimize two different things. And that is something that is known as the concept of Pareto optimality. So we're trying to optimize two things at the same time, which are in conflict with each other. So the best we can do is for each value of one of the two variables, we try to optimize the other ones. So for each number of terms, we try to find the best mean squared error. And if we do so, we would arrive in this case at the red curve. And so this curve is also sometimes called the Pareto frontier. If in this case you are above, then somewhere here, for example, then you're not doing optimally, because you could certainly improve the mean squared error even without changing the number of terms. But if you are on this frontier, then you can no longer improve the mean squared error, that is, decrease it, unless you also increase the number of terms. Okay. So that would be one thing you could do. And in this case, you could say, I have a kind of measure of complexity. I regard the number of terms, the length of my expression, as a measure of complexity. So I'm trading off complexity versus goodness of fit. Okay, fine. Now, there's something else I can do. I could go back to my expression tree and I could say, I have a feeling that some of these operations should typically occur more frequently or should be explored more readily, more likely than others. So in other words, I could imagine that instead of trying out all trees and considering some of them, if they have the same number of nodes, equally good, I could try out some more than others. So I could assign probabilities to trees, and then I could prefer those that have higher probabilities first, even if maybe they have more nodes. And so that makes some sense, because in a certain family of problems, a certain family of functions that you're trying to fit, maybe certain parts of this symbolic expression tree will occur more likely. So we could say that we introduce a prior probability for trees, for symbolic expressions. Which is no longer uniform. And so there would be many ways, obviously, to do this, to define probability distributions on symbolic expressions, but we want to have a simple way. And a simple way consists simply in doing this. I start out with the root node, the highest node, and I pick some symbol randomly out of my set of possible symbols, that is operands or numbers. So in our case, x, y, z times plus divided minus 1, 2, and so on. I have to decide which ones I want. And then I could assign probabilities to them. So maybe x is more likely, multiplication is also likely, but say division is less likely. And then once I have picked this, and this is not a number, but say an operand, I will introduce two new nodes and I will proceed as before. And I can do so in a manner that the probabilities that I now use for these new nodes are again the same old ones. They don't depend on the context. They don't depend on what symbol I put up there. And so these probabilities would be context-free, as it is called. So that would be the easiest way of inventing a probabilistic language to generate these symbolic expression trees. Okay. And so this is something that people try out. And then, of course, each tree comes with its own probability. That is just the product of the probabilities of the different symbols you chose. And so now you can distinguish a more likely expression against a less likely expression. And if you like, you could use as a measure of complexity this probability, or better yet, something that would increase if the probability decreases. And we have learned how to do this when we discussed Shannon entropy. Namely, what we could use is the logarithm of the probability of an expression. Why is this a smart choice? Well, okay, besides the many interesting mathematical properties like the logarithm being additive, it's a smart choice because when we discussed Shannon, we said that in an optimal way of compressing symbols, in this case, trees, you would need this number of bits to describe that particular tree, this particular expression. So if the probability of this expression is very low, then in the optimal coding, you will need a lot of bits. If the probability of this particular tree is very high, even if it has many nodes, then this expression tells you that you need very few bits to describe this tree because you're compressing efficiently. And so that would be a smart way to describe things. And so instead of just counting the number of nodes as we did before, we could also say, no, this is now our measure of complexity. And again, we could draw curves like before. So we could say, oh, how does my mean squared error evolve if I let this measure of complexity increase? And again, I would imagine a curve like this. Okay. So this is all good and nice, and you can go through this, and people have written programs to try to fit symbolic expressions. And they have toyed around with a prior probability distribution, and they have also introduced other heuristics that are maybe more complicated in order to quickly figure out symbolic expressions. It's still a complicated search process, of course. So there are now two difficulties. The first is this prior, as usual with any prior, is a little bit subjective. This particular one, I don't know, maybe I simply claim that the multiplication is more likely than the division, but how do I know? That will actually depend on the set of problems that I then will use it on. So the prior is obviously important. And a little bit subjective. But I can also use it to good effect. So I could then consider fitting many functions, and I could adapt my prior so that the solution terms, the expressions that I get out for these different functions that fit the functions, become relatively inexpensive to encode if I change my probabilities in a suitable way. So I would adapt the probabilities so that the terms that I use very often, they have a higher probability. So I can do these things, I can be adaptive. But the more severe problem is that this is not really a powerful enough approach. So simply by writing down algebraic expressions, I cannot describe arbitrary algorithms that can produce arbitrary regularities or detect arbitrary patterns. This is simply not possible. So there, these expressions are not powerful enough. I need algorithms, I need programs, and this is where we want to go. Okay, so they're not powerful enough to describe interesting regularities. For example, if we come back to these problems, if I even just want to describe this fact that the 0-1-0-1 pattern repeats in an infinite loop, I would not be able to do that using arithmetic expressions, obviously. Okay, so we want to go to algorithms, and to implement algorithms, we want to have programs. And then we have to talk a little bit about how to describe programs. Now, we will be interested in relatively foundational questions. So we are not interested in the exact implementation. So we are not going to talk about practical programming languages. But what we are going to talk about and what we are going to need is Turing machines. So several of you will probably have heard about this concept several times before. I'm not going to discuss it in any detail now. I will just tell you in 5 minutes the things that we really need for what we are going to discuss. So what's a Turing machine? That's a general model of computation, or classical computation at least. So it's built in a very simple way. You imagine you have the Turing machine, you might call it M, which consists of two main pieces. One piece is, so to speak, what you could call the CPU, and the central processing unit for a modern computer. And the other part is the tape. Now, the CPU can hold some memory, but it's very restricted, finite memory. It's like the registers, the actual registers that hold numbers in an actual CPU. So it can be in a number of different internal states according to the values that are sitting inside these registers, if you like. And in addition to that, it also can react to what it sees on the tape, because it has a head that points to some location on the tape and can read the symbol that is stored there on the tape, imagine of binary symbols. And then depending on what it reads and what it sees, and depending on its internal state, it can take some action. So it will have a transition table that tells it, given the state, and given the observation, the internal state, and given the observation, that is what it just reads on the tape, it will take a certain action. And these actions can be that it changes its internal state, that it writes something else on the tape, or also that it moves around on the tape. Okay, and this tape really plays the role of the random access memory that we have in a typical computer, only it's idealized, so it is infinite. And I should also point out there are variations on the Turing machine. So you could have several tapes. Some tapes may be restricted in what they can do. Actually, we will use something like that later, but that's the basic principle. And any algorithm that you can think of can in principle be implemented on a properly chosen Turing machine. Now, some Turing machines may be a bit restricted, but there's the concept of the universal Turing machine, which is powerful enough that it can simulate any other Turing machine. So it can emulate any other Turing machine running on any input. And it does so by having, so to speak, an emulator that it runs, another little program that tells it how to produce the effects that this other Turing machine would have produced. So as the input is now not simply X, the input that we wanted to run. So any other Turing machine can be emulated, but we also have in front of it some, so to speak, emulation software, emulation program, or some description of how the other Turing machine would work. But the important point is that this emulation program is independent of the input and also independent of the size of the input. It always works. And this is not an abstract concept. The same would be true if you buy an emulator software that can emulate a Windows system, but you're running on a Linux machine. So this is a finite sized piece of software. And then you can use it to run any other piece of software that you would have wanted to run on the original computer. So what this means in particular, there's a fixed finite overhead. It depends on your universal Turing machine and on this other Turing machine that you wanted to simulate, but then it's fixed. It doesn't depend on the input. Also, it should be said there are many universal Turing machines and they can simulate each other, and there's always this fixed finite overhead. So that is good, and in principle you can do anything. The problem, there's a problem, of course. There is one problem which is extremely important for us, and that is the so-called halting problem. Now, imagine you are given a program which is just a bit string. So when I talk about a program, it's a bit string that may serve as an input to a Turing machine. You can ask, if I start this program, if it's being executed by the Turing machine, will it run forever or will it eventually stop? So you imagine that this program is being fed as input to the Turing machine. It starts to follow its internal instruction set, and it reads the program and it generates new data on the tape that is, so to speak, the output that it produces. And it produces the first 10 bits of output. And then it takes a longer time to produce bit number 11, and an even longer time to produce bit number 12. And then afterwards, you wait for an hour, you wait for a day, and you're not quite sure. Is it stuck? Is it stuck in an infinite loop? Or will it eventually continue? And that's hard to tell. So the question is, can you inspect the program and tell in advance whether it will be stuck in an infinite loop or not? Or whether it will actually terminate at some point, and this is the output, and now I'm finished, or whether it will run on forever. And so obviously there are simple programs where it would be very easy with an algorithm to identify that there's an infinite loop. If you have something like while true, and then something after that, this is a loop that will run forever. But imagine that the loop depends on a condition that depends on some variable, and this variable is always calculated inside the loop. And then it may already become more difficult. Of course, there may still be cases where a reasonable algorithm could still immediately tell you what's going on. So for example, if the variable starts to be defined as equal to 2, and inside the loop, there's only one instruction that does something to the variable, namely it adds 1 to the variable. And then there is the condition that the loop stops if the value of the variable reaches 10. Then obviously you can conclude, yes, it will reach 10 eventually, and so it will stop. But you can make this more and more complicated, as you imagine. And so the question comes then up, and this is maybe even a practical question: can you write an algorithm to which you give such a program, and which is able to tell you in advance whether this program will get stuck in an infinite loop or will it eventually stop? And so the slightly disappointing answer is that no, there is no such general algorithm that is able to decide this question. Okay, and so that's the famous halting problem that was first identified by Turing. Now, the detailed proof may be a little bit complicated, but the informal proof is very simple. So you just imagine if there is such an algorithm, it should be implemented as a program on a Turing machine, and as some kind of program, let's call it H. And now I will be very nasty, because I will write another program P that contains this H, this program that implements this magical algorithm, that contains this as a subprogram, and then calls it, so to speak, on its own source code. And if the answer of this algorithm is yes, this should halt, then my program P will be very nasty and actually go into an infinite loop. And if the answer is no, this will never halt, then it can do the opposite. So my program is constructed such that it always will contradict whatever the algorithm says. And so that kind of shows in an informal way that you cannot write such an algorithm that can decide this question for an arbitrary program. It may still work for many different programs and for some very easily, but it cannot work for an arbitrary program. Okay, so that's the famous halting problem, and that's a serious difficulty. So we will see how this comes back to bite us a little bit, because if you then ask questions like, what's the shortest program that does a certain thing, you immediately want to try out one program after another. But unfortunately, some of these programs may basically run forever, and you are not quite sure, are they stuck? Will they really run forever? Should I interrupt them, or will they eventually provide an answer? Okay, so that's the halting problem. So there is one other thing that we should discuss about Turing machines, and that is a little bit more specialized. It comes back to something that we, I think, had briefly discussed when we discussed channel entropy and compression. So suppose you want to compress a long sequence of symbols. Now, each of these symbols in your compressed version will be represented by a binary code word. So code words are binary strings, like the ones shown here. And then you will string one after the other together many of these code words. So if you have a big file composed as a sequence of many symbols, you will run your compressor, and then you will get a sequence of code words. and that's the compressed version of your file. Now, you want to have ideally one nice property. So if there is the final compressed version of your file and it looks like this, what you want is that you immediately know which pieces are the code words. You want to know, aha, this is a complete code word, and that is a complete code word, and that is a complete code word. And you want to know this without introducing an extra delimiter between them, because if you really want to store this delimiter, it would use up extra memory. So it would be good if these code words can stand on their own and you can just string them up in a long sequence. And you immediately know for every code word when it is finished. And so there's a particular name for this. These are the so-called prefix-free codes. Why are they called prefix-free? Because no code word is the beginning of another code word. So no code word is a prefix of another code word. For example, in this example, 110 never occurs as the beginning of any other code word. If it did, of course, it would be bad, because after reading 110, you don't know whether you have to stop or whether you have to read on. So these are prefix-free codes. No code word appears as the beginning of another code word. There are many ways to construct such prefix-free codes. One extremely simple way is shown in the first example up here. So that would be, say the 0 is called as a stop bit, so it only occurs at the end of each code word. So automatically I know when the code word has ended, and because I know this, none of these code words will be the prefix, the beginning of another code word. But that's it's very wasteful actually, because you see for any number of bits, I only have always one code word. That's not very smart. There are many other ways to do this. For example, I could say, I do something similar, but I always group together bit sequences of 2. And then when I have 2 bits, there are 4 possible combinations, 10, 01, 00, 11. And what I would do is I reserve maybe one combination as a special marker that tells me the end of my code word, and all the others I can use to encode information. And then again, I can do similar things as before, but now I have more freedom. So every piece of 2 bits has 3 choices that it can still go through, no problems. It only should avoid the 11 because that's the marker of the end. But I can also do many other things. For example, I could say that there's always 5 bits that are completely free. And then the next bit is crucial. If it is 0, then I will stop. If it is 1, I will go on, and I will again have 5 bits that are completely free, and then I stop, and so on. So these are all examples. So these 3 sets of code words are all examples of prefix-free codes. And they are important in the more general theory of Turing machines, because they have many very nice properties. And so what people often want to consider is that every input, every program fed into the Turing machine is represented as such a prefix-free code word. So each of these code words now would represent the entire program. And what this very simply means is by reading the program from left to right, you immediately know when it stops, and then it's over. And really the same happens on your hard disk. Maybe there's an end of file character, or maybe at the beginning of your program, there's some special storage area that tells in advance the length of the program to follow. But in any case, the computer knows when to stop. Now, there is one very, very interesting fine property about these prefix-free codes, and that is the following. Imagine, let's say P is any of these code words, and L of P is the length of this code word in bits. And now I do the following. I take 2 to the minus the length of P in bits, and I sum this over all my code words P that are part of the prefix-free code. And so there's a famous inequality that says if you sum this all up, you don't go above 1. Maybe you get exactly 1 or you are less than 1. So it can almost be interpreted like a probability distribution over these code words, because it's normalizable. Yeah? And so this has a name. This is called Kraft's inequality. And you can check it for all these examples, which I did for myself, and you find this is actually true. So that's nice. Okay, so this will return later, but not immediately. So this was Turing machines in a nutshell. And now I want to really dive into estimates of complexity that rely on programs, regularities discovered by programs. Is there a question so far? Okay, so let's start out with something that is called algorithmic complexity. And later we will generalize this somewhat. So it started out in many different ways and by people asking different questions. The names particularly associated with it are Kolmogoroff, the mathematician, and Solomonov and Chaitin. And one of the questions that were asked, this particular one was asked especially by Kolmogoroff, was if someone gives you a table of random numbers, let's say random bit strings, how do you tell whether this is random or not? Obviously, if all these numbers look like 0, 1, 0, 1, 0, 1 with a regular pattern, that doesn't seem like a good table of random numbers, and maybe you shouldn't buy it. So how can you tell? How can you tell how random this is actually? And so the idea that Kolmogoroff had and Solomonov in a different way was the following. Let me try out all possible programs on some Turing machine and see whether they will output this bit string X. So I could check out all possible programs P, such that when I run my universal Turing machine with this as input, with this program P as input, then the output would be X. And now I'm interested in particular in very short programs, obviously, because if I can find a short program, that means there is some regularity. So what I want to consider now is I want to consider all such programs, but for every program, I want to calculate the length of the program in bits. And then I want to minimize this over all possible programs. So find the minimum length program that can describe my output X. And that is what is now often called Kolmogoroff complexity or algorithmic complexity. And obviously, it does depend on this universal Turing machine. So we will immediately discuss the pitfalls. But the first thing that comes to mind is obviously this must depend on the machine you are choosing, because that's not very abstract. So imagine you have an algorithm and you implement it in one programming language and it is quite short, and you implement it in another programming language and it is longer. For example, if you implement it in C, it's relatively short. If you implement it in assembler, it's pretty long. If you implement it in Python, maybe if it's even shorter. And maybe the shortest program you will get in a programming language where this particular algorithm is part of the built-in set of functions. So the question is, what does such a definition even help us? Yeah, if it does depend on the Turing machine that I have available, which may have a lot of built-in power possibly, so it can take shorter programs and still produce the same output. as another Turing machine with a longer program. But here, what comes to our help is this universality of Turing machines. So in order to describe what goes on in another Turing machine, you only need this emulator program. And this is a fixed length program that you have to run. So if you then ask for the minimum length, then yes, the minimum length may differ between two Turing machines, but it will not differ by more than the length of this emulator program. So what is shown is that the Kolmogoroff complexity for some universal Turing machine U on this string X and the complexity on another machine U prime, they may be different, but they are different by a constant that does depend on U and U prime, but it does not depend on X. It does not depend on the bit string. Yeah? It's just this fixed emulation software that you need to account for. Okay, so that's a good thing, because in particular, it means that at least if you keep two machines fixed and you consider longer and longer bit strings X and you want to learn something about their regularity or the absence of regularity, then the answers you get are up to this constant actually identical. So for example, if this is a completely random bit string, then the best program you can find will simply be growing like the length of this bit string. And this is true regardless of which universal Turing machine you choose. Maybe one of the universal Turing machines that you're looking at is a little bit nasty because it has built in a special command that would allow it to print the first 1,000 bits of this particular bit string X. So that's possible. That's entirely possible. And then that would be a very short program for these first 1,000 bits. But afterwards, this is fixed. Yeah, afterwards, if you consider even longer and longer bit strings, this doesn't help you anymore. So in this sense, the Kolmogoroff complexity is well defined, and in this sense doesn't depend on the choice of machine. So what's the basic idea? So now that we have covered this, the basic idea behind this concept of Kolmogoroff complexity is, of course, compression. So the same spirit that we discussed when we discussed Shannon entropy. So you think that if you can find short programs, that means you can compress the bit string very much. Then, of course, it has a lot of regularity and it should not be considered random. Whereas if the amount of information you need to store in terms of the program to describe the bit string just grows with the length of the bit string, then obviously it's a random bit string. Okay. So it's all related also to compression. And now here comes the big killer, so to speak. The killer is the halting problem, because the halting problem means this is uncomputable in general. And the reason is, of course, here we are asking for the length of programs, for the minimum length of any program that would produce the right output. But now suppose you are trying out a relatively short program, but instead of printing out all the bits, it prints out the first 5, they match, that's great. And then it gets slower and slower and even slower, and you're not quite sure, will it still give the right output or not? So that's the problem. Nevertheless, so we will see how this problem can be overcome by some modification and some smart approach. But nevertheless, there are some properties that can still be shown in general. And I just want to mention One of them, there is an upper bound. Upper bounds can be established, yeah, because you just have to give a program that does reproduce this bit string and that runs and that doesn't go into an infinite loop and that produces this bit string. And then the length of this program is an upper bound to Kolmogoroff complexity. Maybe there would be a shorter program. Maybe it's among those programs that seem to take forever, but at least you have an upper bound. And so there is a simple upper bound, which is basically just the length of this bit string plus a little bit of overhead. Because if you think about it, you have to probably say something. So the type of program you would use is basically just saying, I store this bit string X in my program, and the program just says, please print this bit string, but it has to store a little bit of extra information, and that's why there is this little overhead. There's also another interesting mathematical theorem. I don't know the proofs of this, but there's another interesting mathematical theorem that says K of X is even at least L of X for most X. In other words, most bit strings basically are like random bit strings. If you pick a bit string at arbitrarily, then you will not really discover some interesting patterns. Now, what this means philosophically is another question, because obviously science works, so we do discover patterns in reality. Okay, so that's an obvious problem. It's uncomputable because we cannot try to find a program that gives us the desired output. So let's be more specific with this. Yeah. So our goal could be simply to find a program P that outputs some desired string X. Okay. And so the naive approach is just I run all programs P of increasing length. So I imagine I start with a very short programs, say programs that are only of 1 bit length, 1 or 0, and then programs of 2 bit length and so on. And people imagine in this kind of game that you have encoded these programs in this prefix-free code form. So run all programs P of increasing length and always check whether they output the right output. And of course, we already learned, no, this doesn't work, because it could be that the third program you try, so say the first 2 programs don't produce the correct output, and the third program settles into an infinite loop, but you're not even quite sure whether it really does, and so that's bad. Okay, so that would be the naive approach. And the question is, can we circumvent this? And so the way to circumvent is to slightly modify the problem. We will modify it in a way that we will prefer programs not only that are short, but also that are running relatively fast, so that are short and fast in a well-defined way. Okay. But before I move there, that's the so-called universal search algorithm. Are there any questions already? Okay. So let's just move. Aha. So suddenly there are questions. Okay. Is the lower bound for complexity empirical? No, this, I couldn't give you the proof now, but I can provide you with a reference. So that's a mathematical theorem. So that's not empirical. But of course, you're welcome also to do, well, so there's mathematics behind it. What does it mean by most x? Oh, so there must be a probability measure defined on x. So take the uniform measure. So among all bit strings of length n, you say each bit string is equally likely. And then you can define what it means. And you would consider longer and longer sequences. And then you would define, like in probability theory, what it means that the statement is true for most x. So I think there will be some epsilon delta argument. So I would be able to give you the reference where this is then precisely defined. Yeah, so good question, like with almost always in the sense of measure zero. For that to work, you can obviously not consider finite bit strings of finite length, because then there's just a finite number of them. Then you would have to take the limit in a suitable way. And maybe then it's the same as almost always. Okay. But good questions. Yeah, so these are non-trivial theorems, but at the moment they are still dealing with something that we cannot even compute in general for arbitrary x. So we have to find something better. Okay, so we will now modify the problem to get something tractable. And so in words, our goal will now be to find a program which is both short and fast, and we will trade these off against each other. And of course, again, this program should output x. More precisely, the algorithm that we're going to discuss is even somewhat more general in an interesting way. Namely, you could say, whenever I get some output, I could apply some function that I can quickly evaluate and check whether this function returns true or is then equal to some other value y. So we want to find a program that produces an x that fulfills a certain condition. Okay. And so this is very powerful, because if you think about it, so this is in general called an inversion problem. You have a function phi and you want to find an argument such you would get x. But if you think about it, this is so general that a lot of what we're interested in can be formulated in this way. So for example, equation solving, obviously, so this is already equation solving. But also, for example, symbolic integration. So x could be a description of a symbolic expression, and phi could be a function that takes this expression and calculates the derivative, and y is another description of a symbolic expression, and you then want that the derivative of x is equal to y. So you are basically finding the integral of y. Okay. So this is the more general version to view this. So now, how does this universal search algorithm work? So it proceeds in iterations. one of the main concepts is that it will start programs and then let them run, but not wait for them to finish, but already start other programs in just a smart way. So I will now describe this algorithm. So let's say we have iteration number L. And at this iteration, we will execute every program with a length that is at most L, but instead of meaning I want to run it and see when it finishes, because maybe it does never finish, I will just execute it for a fixed number of time steps, like in a multitasking system on a computer, where every program gets its share of the time. And the number of steps that I give it depends on the length of the program. Shorter programs get more time steps. And so what I mean by that is, maybe it's good to graphically visualize this. So there would be a short program and here I will denote on the horizontal axis the number of steps that the program has been running. And so this short program is run for a short time, then for a longer time, then for an even longer time, and these times grow exponentially. Then there would be a longer program because it is longer. In the first few iterations, it was not even started yet. And only later it starts and is run for a short time and then a longer time and so on. And so you see now the principle. You have longer programs starting later and having a smaller fraction of the time, whereas shorter programs start earlier and get a larger share of the time. And that's a good way to trade off the length of the program and the running time. Still, it could be that the short program never stops, goes in an infinite loop, then it will still continue running, but at least I will also try out the longer program. So that's the idea. So this is one way of plotting things. I can also say, here I plot the number of steps in this iteration number L. And here I plot the length of some program. Only programs with a length up to L are executed at all during this iteration number L. And the shorter ones are getting many more steps. So there's an exponentially rising function there. So we absolutely prefer shorter programs. Okay. So now we want to see how this works out. So one of the things we want to learn is, do programs actually run until arbitrary times? Because if you would set up this algorithm in the wrong way, you could have a situation where you start more and more of the longer programs and they use up all the time. And then the short program that has started maybe even earlier doesn't get a large share of the time anymore. And if this share of the time that it gets decreases exponentially, it will never execute until the finish line. So it will be stuck. It will take longer and longer and will be stuck for this reason, not because it's a bad program, but because there are so many other programs that are trying to run. So now we have to calculate how the total running time behaves and which share of this total running time is really assigned to a given program. But first, again, is this clear what we are doing here? So there will be an iteration L equals 1, then we only run all programs of length 1, then L equals 2 until length 2 programs, continuing also the older programs that have already started, and then iteration 3 and so on. So each iteration continuing all the old programs, giving them a large share because they were shorter, but also starting new programs, which are the longer programs. Okay, so let's have a look at how this goes. So let's first calculate the total number of steps in iteration L. So when I talk about steps, you can think of it really like nanoseconds on a real machine, so to speak. So I will call this delta TL. And of course, I just have to sum over all the programs that are eligible to run in this iteration. So that's all programs with a length up to L. And then the number of steps that they run, which is 2 to the L minus L of P. Okay. And so, okay, here's something I should say. Possibly one of these programs has already halted. Yeah, maybe it already produced its output. Then, of course, it wouldn't be included in the sum. So I should have an inequality here. Okay, so that's one thing. And then there is an interesting point here. So that's that's where we need what we learned. So the programs we're discussing here are supposed to be programs represented by a prefix-free code. And if that is the case, we can use our Kraft inequality. So the sum over 2 to the minus L of P, that is then less than or equal to 1. And the 2 to the L is, of course, just a prefactor. So the 2 to the L survives. So this is what we get. So this is the worst case. It may be faster, but this is the worst case. So this number of steps that we take at iteration L grows possibly rapidly, namely exponentially. It may grow slower, of course, if many of these programs halt, but it can grow exponentially. Okay, so that's the steps in iteration L. And as the next obvious question is, what's the total number of time steps we have already spent in our calculation up to this L? Okay, so the total steps is, of course, just the sum over all these delta TL. And well, if I didn't make a mistake, that's just 2 to the L plus 1 minus 2. Just summing up the powers of 2. And so if L is large enough, I would just get 2 to the L plus 1. And of course, again, this is the worst case. Because again, some of these programs might have stopped and we had this inequality before. Okay, so that's the total running time, grows exponentially. What are the total steps for a given program? Now we focus on a given program that we're interested in, because maybe this is the program that gives the right output eventually. What's the total number of steps for this program P up to this point in time? Well, so let me call this tau. That's just the sum over all iterations in which this program was eligible to run. So starting from iteration L of P and going up to L, and then the number of steps it got. Okay, so if, again, I didn't make a mistake, this would be 2 to the L minus L of P plus 1 minus 1. So in the limit of large L, we can leave away this one. So again, this is something that grows exponentially. So that's nice. And now I want to imagine that this is really a good program. So after a certain number of steps tau, it would print the correct solution. And what I want to know is, in terms of real time, as all the other programs are also running and eating up the time, in terms of real time, when will this happen? So that's the total time your computer has been running until this point. And well, the only thing I have to do is set this tau of P, which is the time until the correct solution, equal to the tau of L comma L of P, which is the time that such a program has been running until L. And I can use this as an equation to get the L, the iteration at which I will finally get my correct output. So this was 2 to the L minus L of P plus 1 up to this little additive constant. And so what I will get is 2 to the L equals 2 to the L of P minus 1 times tau of P. I'm a little bit sloppy here because these iterations come only in integers, so maybe I have to round, and then there's maybe a plus 1 somewhere. But these are, so to speak, more the details. And so now we can have a look again at our total runtime. So the total runtime scales like 2 to the L plus 1. So I can plug in this total runtime here, and I can say total runtime until the point where I get the right solution is, well, smaller than or equal this 2 to the L plus 1. Remember, this was the worst case. And so from this equation, I see what this is. So this is 2 to the L of P times tau of P. And if you look up the correct results, doing all the approximations correct, there would be another plus 1 in the exponent here. So 2 to the L of P plus 1. Okay. So this is an important result. So what it means is this universal search algorithm will eventually converge. So if you have a program P that solves your problem that would output a correct solution X, this universal search will find it. And the time it needs, despite running all these other programs, grows linearly in the time it needs for this particular program to run and output the correct solution. Unfortunately, of course, there is a prefactor. The prefactor does not depend on the running time tau of P, but it does depend on the size of the program. And this prefactor is exponential in the size of the good program P. So it's exponential in the length. That's the downside. But at least it's linear in the running time. Okay. And of course, this exponential factor simply comes from the fact that we're still trying something a little bit crazy. We're trying all exponentially many programs to see whether one of them works. We're doing it a smart way, so we are not getting stuck because any program that hangs up, that runs forever. And we are preferring somewhat the programs that have a good balance between being short, but also by not needing too much runtime. Okay, so that's universal search. It was only discovered at the beginning of the 70s. And that's an important discovery in algorithmic information theory. And so this is now something that can work. It's still using a lot of resources, but at least we're not getting stuck. Okay. So if there are no questions, we can raise a question here, namely, we had this Kolmogoroff complexity first, and it did prefer the shortest programs. Now, in light of what we are seeing here, should we maybe introduce another measure of complexity that also takes into account runtime? Can you trade off the time and space dependencies? Very good question. Yes, I think you can by modifying the algorithm, how you allocate the resources. I even imagined I could use the lecture to spend a bit discussing this point, but there's so much to say. So you can allocate the resources differently. You must be very careful. If you do it in the wrong way, you can actually come up with algorithms that where any given program only overall, even up to infinite time, gets only a finite number of steps allocated. This would be terrible, of course. But if you do it right, I think you can reallocate the dependencies. I wouldn't know immediately a good reference for that, but I think it's possible, yes. Okay, so complexity measures. Kolmogoroff just says, give me the shortest program, shortest L of P. Now we can say something more reasonable. So imagine I have two programs. So maybe there's a program P, which has some length L of P and some runtime T tau of P until it prints the correct output. And then there is a program P prime with another length and another runtime. And both of them print the correct output. And the question is, which is completed first? Because that's when my universal search, at least in the simple version, stops. Yeah? Which completes first? According to my algorithm. And so I would say P completes first if 2 to the L of P times tau of P is smaller than 2 to the L of P prime times tau of P prime, yeah, because that was the runtime according to universal search. And so we will first encounter, or we will first pick the P, the program, that minimizes this particular combination. Okay, and minimizing this combination, I can also rewrite it. If I want to come closer to Kolmogoroff complexity, maybe I should take the logarithm of this expression. And so I would then say you minimize L of P plus the logarithm of tau of P. And so this becomes a natural generalization of Kolmogoroff complexity. You have L of P, but also the logarithm of the runtime. And so this is called Levin complexity in honor of Levin, who invented universal search. So the Levin complexity of some bit string X is also sometimes called KT for Kolmogoroff complexity that includes some time information. KTX equals the minimum of overall programs, not of the length, but the length plus the log of the runtime. And just like Kolmogoroff complexity, again, it's dependent on the universal machine. And again, different machines can give slightly different values, of course, but they are related by this constant offset. And the advantage that we have now is that this can be computed. We have an explicit algorithm actually to compute it, in contrast to the Kolmogoroff complexity. So that's very nice. That's very good. And it does make practical sense. And so now I want to, I hope this is clear. I think it should be pretty clear. Now, there's a slight generalization you can come up with. And that comes back to what we said when we discussed symbolic expressions. We said, maybe we want to pick different symbolic expressions with different probabilities by introducing different probabilities for certain terms in the expressions. We can do the same for programs. We can introduce probability distributions over programs. Maybe some programs are somehow intrinsically considered more likely than other programs. So that can give a slight generalization of this concept. So I could have capital P, that's probability, of little p, that's a program. And that would be a prior distribution over programs. Now, if I'm smart, I compress these programs. So I use optimal compression. And then, of course, I know that a program P will be compressed to something that has a number of bits that scales like the logarithm of the probability. So P will be compressed to some P prime, where the length of P prime goes like the logarithm of the original probability. So that's Shannon, so to speak. Yeah, I can compress like this. And these new programs, the compressed programs, they look like random bit strings where 1 and 0 occur with 50-50 probability. So that's the feature of optimal compression. Now, of course, I can apply Levin search to these kinds of programs in principle. And so if I then minimize, I'm just sketching these things, but if I minimize 2 to the L of P prime tau of P prime, what I'm really doing is I'm minimizing tau of, in terms of the original programs, tau of P is the same as tau of P prime because they are functionally equivalent, they do the same thing, divided by the probability of P. Yeah. So this 2 to the minus L of P, that could be interpreted as the probability of P if I have a uniform prior distribution over programs where a bit 0 or 1, that's always 50-50. If I don't have this uniform prior distribution, then I can be more general. And then if I apply Levin search to this more general situation, I would say that it is looking for programs where this particular ratio is minimized. So the runtime divided by the probability. If I have a very unlikely program, then of course that's bad because even for short runtime, this ratio will be large. Okay. So this is all I wanted to tell you today. And then next time we will actually take this one step further, because at the moment we are only asking for which program outputs a certain bit string to say something about the complexity of this bit string. And next time we will use this for a method of induction. So you have a maybe infinitely long bit string, you observe the first few bits, and you want to come up with a smart model to predict what happens next. And you don't want to make too many detailed assumptions about prior probabilities of different models. And so Solomonov came up with a general theory with basically no input, and based on this theory of Turing machines generating bit strings. Okay, any questions for today? Well, if there are no questions, think about things, and then we meet again on Wednesday for the last time in this lecture series. See you on Wednesday.